We're going to start our introduction to limits by talking about velocity. Specifically, average velocity versus instantaneous velocity. The average velocity is the velocity you go over a period of time, whereas instantaneous velocity is the speed that you're going at the moment you look at your speedometer. Let's look at an example. Let's throw an apple into the air. If we neglect air resistance, the formula that models the distance over the ground of the apple as a function of time is as such. S of t is equal to negative 16t squared plus 96t, with s being the distance in feet above the ground and t is the time in seconds. What's the average velocity? Well, that's simply the change in distance over the change in time. Let's look at two specific examples of this. Let's find the average velocity between t equals 1 and t equals 3 seconds. S of 3 minus S of 1 divided by 3 minus 1 would give us that average velocity. Let's go ahead and plug in 3 and 1 into our equation. Once we go ahead and plug these values into our calculator, we get 144 minus 80 divided by 2 equals 32 feet per second, and that's our average velocity between those two times. Let's look at between two different times. Let's look at between t equals 1 and t equals 2. So the average velocity between 1 and 2 seconds is a different number. If I plug in s of 2, and the denominator is now 2 minus 1, I get 128 minus 80 over 1, or 48 feet per second. So why do I get two different average velocities? Let's look at the graphs to see if we can figure this out. So I've gone ahead and graphed this equation. I've used a program called Desmos. It's free both on mobile devices as well as computers. So here's a line between the times 1 and 3 seconds. What's interesting is if I calculate the slope here, I in fact get the slope of 32. So that line that cuts through my graph at the points 1 and 3 in terms of my x variable, that slope is equal to the average velocity. Let's look at our second example. If I zoom in at the graph when t equals 1 and t equals 2, I find the same thing. If I calculated the slope, I would find it to be equal to the average velocity I found. I'm going to define what I mean by this line that goes through a curve at 2 points. That's called the secant line. In fact, I can now say that the average velocity, VAV, is equal to the slope of the secant line. That's m subscript secant, and that is again s of t1 minus s of t0 divided by t1 minus t0. So that's average velocity. What do we mean by instantaneous velocity? Well, instantaneous velocity is what happens when t1 actually equals t0. That is, I want to find the average velocity at a moment. Well, we can't do that, at least not by this formula, because if we did, we'd be dividing by 0, since t0 minus t0 would be equal to 0. So let's see how we're going to talk about that. So instantaneous velocity is the velocity at a single point. Let's focus on our example, finding the instantaneous velocity at t equals 1. So we've already looked at two different intervals. We've looked at from 1 to 3, that was an average velocity of 32. We looked at 1 to 2, and that was an average velocity of 48. We could continue to do this. We could get closer and closer to our instantaneous velocity point we're interested in. That's 1. So I've gone ahead and calculated V average between 1 and 1.5. To remind us, I've put the formula for V average there, as well as our specific function S of t. So I could keep going. I could get closer and closer to 1. And if I take the absolute crazy step of plugging in 1.000000001 minus S1 divided by, well, what you have in the denominator, it gets really, 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 really close to the number 64. So I'm willing to wager that the instantaneous velocity at 1 actually is 64 feet per second. But I wouldn't want to just attack this from above 1. I'd also like to look at values below 1. And I'm not going to bore you with showing all the calculations. In fact, to be honest, I've now put this in an Excel spreadsheet. But if I looked at 0.9 to 1 and then 0.5 to 1, that is 0.9 seconds to 1 second and 0.5 seconds to 1 second, at 0.9 I'm still pretty close to what I think that instantaneous velocity is of 64, but as I get further away from 1, I get a larger difference between the number 64 and the average velocity at that time. So the question is, what does this look like graphically? If we look at the graph of the line with slope 64 at 1, it looks like that actually isn't a secant line. That is, it only seems to touch the curve at a single point. Well, that line is called the tangent line. So now I'm going to get a lot more technical in how we talk about this word approach. We're going to specifically now talk about limits. So the slope of the tangent line is equal to the limit as t approaches 1 of the slope of the secant line. And we can replace the slope of the secant line with the equation s of t minus s1 divided by t minus 1. And just like the secant line slope defined the average velocity, the tangent line slope tells us the instantaneous velocity. And before we end, I'm just going to draw what I mean by this limit as t approaches 1. T can approach 1 from both the negative side, the left-hand side, or the positive side, the right-hand side. The limit is when that number is approached from both sides and it equals a particular value. In our example, this equaled 64. And this is the general concept of what a limit is.